My name is Joris Kortstee. I work for Danfoss Industrial Refrigeration. And today I talk about industrial refrigeration systems and specifically how the systems are built. Industrial systems are basically flooded systems. So pump circulating, so it's not expansion valve, there's no superheat. The good thing about that is that you have a low delta T between the evaporator and the ambient temperature. So it's very efficient. The systems are pumped, so it's very robust. The refrigerant itself is ammonia, most of the cases. Ammonia has a very high efficiency. The thermodynamic properties are super good. It's a natural refrigerant. The global warming potential is 0. Ozone depletion potential is 0. So you would say, what is wrong with the refrigerant? Well, nothing wrong, but it is classified as toxic and flammable. So the industry tries to get the charges down. And there's many ways of doing so. And since the last decades, I would say people try to limit the charge. And it's often done with CO2 as another refrigerant, as a secondary one. And I try to explain a few examples, how you could build them, the pros and the cons. I cannot be completely complete in such a small presentation, but I think you will get the point. All right. So this is an example of, let's say we have an ammonia system in Europe, typical charge, 5 kilogram per kilowatt. So this is a 4 megawatt system, 20,000 kilogram. So if you do nothing, you have one system, one charge, and you just try to make sure that it is as safe as possible. The other thing you could do is split it up. So you split the system in half or in 3, and you mitigate basically the risks of the ammonia systems. Another way of reducing the charge is ammonia DX, because then you don't have the flooded part in the suction line. You can go really down in charge. So for instance, here you could go to half of the charge. A very popular system is the cascade system. So ammonia on top, small system, small charge, high capacity, CO2 pumped around in the second stage. Very popular, very robust. You save a lot of ammonia, to be honest, in charge. The next one is separate low charge ammonia systems. Is it me or? Yeah. Several self-contained ammonia systems on the roof, and the charge is really reduced even more. The last one is no ammonia anymore. And we see this more and more in bigger systems that CO2 transcritical takes over the smaller capacities, like 1, 2, 3 megawatt of the systems. So here we completely eliminate the charge, so there's no ammonia anymore. Okay, so here are the systems. So this one is the typical reference ammonia system. We have medium temperature separators, low temperature separators, and pumps. So you pump more ammonia through the system than you really need. So you have flooded systems. Here we have low temperature ammonia compressors, medium temperature. So this is the reference system, very robust, works very well. And this is the system that we compare everything with. The next, The next system is basically the same. So we still have ammonia on the medium temperature charge, but we have a CO2 system below that. So here you reduce the whole low temperature system with ammonia charge. It's only CO2. The downside, of course, is you have CO2 as a refrigerant, but the pressure are much higher, so you have to be aware of that. And in this case, you also need to rectify the oil again, because in a flooded system, the oil remains at the end of the day in a separator. So how to get rid of it? So you need to rectify it. So the bold words in all these columns are the changes of the one before. Okay, so this is the first way of doing it. The second way is, say, I keep the ammonia on top, I keep the low temperature here, and I change the ammonia part into brine. It's a very, how to say, simple way of reducing the charge, but you could say the efficiency, what happens here, because now we have two heat exchangers in the system, and of course a heat exchanger reduces the efficiency. But the good thing is you can really reduce the charge, like 70 to 80%, which is good. But of course, the running costs are higher because majority, this one here, is simply not as effective as ammonia or CO2. Then we have another one. It looks the same, but this part is changed by this one. And that's a DX system. And that we often see if the capacity here is low and it doesn't justify the cost of a flooded system here. So that's another way of doing it. And of course, because you run with DX, there's superheat. And superheat means that you need to have a lower suction pressure. And then the efficiency gets lower. Okay. Now we go to another interesting one. Ammonia on top and everything below is CO2, flooded systems. It's relatively simple to build, but of course you still have the cascade heat exchanger here. So the only downside, I would say, is that you have the efficiency loss here because of the heat exchanger. But for the rest, the way of building it looks like ammonia. You have to weld, but the only thing is the pressures here are of course higher. But the way you build is kind of the same. Another system that you can do is the same as this one, but you change the flooded LT system in direct expansion. And of course you get some efficiency loss here. This is often done if the low temperature load is low compared to the medium temperature load, and otherwise it doesn't justify the cost of building this system. Now we come to the interesting part. No ammonia anymore, only CO2. So then you have to do transcritical booster systems. This is a DX system that we see from supermarket and basically heavy commercial systems as well. Some characteristics is DX, it's commercial mainly. There's no ammonia anymore, but because we are sometimes in a transcritical state, transcritical phase, the efficiency really depends on the ambient temperature and the place where you build the system. So geographically, where is the system built? So that could be a negative thing, but you have to be aware of it. And this is DX, so you have superheat. You have to have superheat, otherwise how to control. So you have some efficiency loss because the more superheat, the more delta T you have across the evaporators. But this one, it looks the same, but it is a transcritical cycle on top and an industrial flooded cycle here. And this could be a very interesting situation for larger systems because you have to imagine it could be 40, 50 evaporators, and then the system has to be robust and relatively simple. And this is relatively simple. You just have a pump, you open the valves, close the valve, and that's rock solid, I would say. But of course, the downside is you have to recover all the oil, so you need to rectify it. You need pumps, you need separators, so the first costs are probably higher. Okay, this is a busy slide. This is how to explain, how does a flooded system work? So here we have the transcritical cycle. We have, for instance, the high pressure receiver, the medium temperature compressor, the parallel compressors, and the low temperature compressor. So what happens? We have liquid, CO2 liquid. We expand it into the medium temperature separator. That's this line. And then again, we expand it again to the low temperature separator. And that's this line. The pumps pump it around like this and like this. That's this cycle here and this cycle here. And that basically describes in a nutshell what happens. We separate the liquids. So if we have liquid from here and we expand in this receiver, then we are here, we expand it, and we have pure liquid and pure gas. And in the LT separator, we have the same. We expand it again this way, this way. It looks complex, but at the end of the day, it's a relatively simple system. So what should we do to make sure that these larger systems can be built? Well, we are working on quite some solutions. So this is the overall system again. We have a rack, transcritical rack. We could have another one if you like. The compressors become really big. So with one rack, you could probably do 1, 2, 3 megawatt, relatively simple. The problem is if this is going to be bigger, everything has to be big. So components have to be bigger. So that's the first thing that we have to look into. And that's what we did. So we have launched a series of stop valves and filters, size 50, 65, 80, and 100, to be sure that we can cover this part of the system. So now we can offer these valves for racks, for OEM racks, to support these larger capacities. That's one. Then we need much larger high pressure expansion valves. So these are motor valves. We have the ICMTS 20, maybe you know. It's a relatively small one for commercial, but now we need a bigger one. So now we are working on large motor valves, and they are placed here as high pressure expansion valves, this one, or we can use them as gas bypass valves. And especially if you are in a transcritical state, we all know that the amount of flash gas that you create is quite high. And then you need big gas bypass valves here to get rid of this flash gas. That's what this valve is going to be. So for the expansion valve, we can do 2, 3, 4 megawatts, something like that. And for the gas bypass valve, we can do probably half of that. So this was a valve that was really needed to support these larger systems. Also, I put in some ejectors here. So what is an ejector? An ejector is basically an expansion valve, but it harvests the expansion energy. So it can suck, in this case, some gas from any part of the system to support the medium temperature compressors. So the expansion valves are here, and we get an automatic suction flow through the ejectors to support the medium temperature compressor. So you get a better efficiency. COP is going to be higher. But also here we need much bigger ejectors than available on the market. So we have it on the booth. You can look at it. It's a 600 kilowatt ejector, and the idea is that you mount a few in parallel to get the total capacity. So we have high pressure ejectors, high pressure lift ejectors, and low pressure lift ejectors. It depends on the situation what you want to do. But you also have to control all this system. That's what we're also working on. So we have controllers to control flooded systems, evaporators. That's the EKE 400. We can do pump circulation, we can do DX, we can control the room or the medium temperature. We can do all kind of defrost, fan control, suction control. So it's a complete industrial controller that we already have for such systems, both for ammonia and CO2. Then you also need to control these separators. So you have to control the liquid, you have to control the pumps, cavitation, pressure difference, everything you need to control. We have this kind of ready. We are going to launch it probably beginning of next year for CO2 and ammonia. And then oil management. So all the oil that collects at the end of the day here, we have to rectify. So a small part of it we send through an evaporator. You can accumulate the oil in receivers, and then you press them back to the racks. So you need to have a proper oil management. Also that we are working on. And last but not least, hot gas defrost. Hot gas supply. If you want to do bigger systems, there's no way to not do hot gas defrost. That's the most efficient way of defrosting these systems. For that reason, we have in mind separate hot gas compressors to produce a controlled pressure and flow to defrost all these evaporators. But you need some controls for that. So that's all what we are working on to support these bigger systems, transcritical industrial systems. Yeah, here. Okay. So the conclusion is, what can we conclude? Ammonia is still the preferred refrigerant for industrial refrigeration, but we see that more refrigerants like CO2 also are kicking in for good reasons. So we don't know. I have no crystal ball. I cannot predict the future. But because of the fact that the compressors become much larger, the components are available much larger, it could easily be that a transcritical flooded system between 1, 2, 3 megawatt is becoming a solution for industrial systems. And that's my presentation. Thank you. I don't know if you have questions or... Sorry.
Hello, Bridget Rakeshaw from Lubrizol. I just had a question. What are the lubricant considerations that you have to have in the ammonia CO2 cascade systems? Yeah. So those can be considered very different refrigerants as it relates to the lubricant compatibility. So is there any special consideration that you would have to take into account in that combination system when compared to the individual ones?
It's a very... Because what you have is a cascade heat exchanger between ammonia and CO2. So you have a loss, you have a heat transfer loss, no doubt. But the only problem you could have is if there is a leak in that heat exchanger, then you get ammonia carbonate. And then you have to clean the whole system. And I have to say, especially in the beginning, like 2004, 5, 6, 10, this technology was maturing. So yes, of course, leaks happened. But I can say it's quite mature. There's all kind of technologies to produce these heat exchangers. And I think they're pretty mature now. So there's basically that risk is basically gone. That's a good question. Yeah. More questions? Then I want to thank you.